Good morning. Get ready for some physics. Think of a rock sitting on the ground. It's in equilibrium. It just sits there forever until it's picked up. To a scientist, this is really interesting because in physics, Isaac Newton had us start looking at forces in nature. And to be in equilibrium, the forces have to balance out to zero. And we know that the gravity of the earth is pulling down on that stone. What's pushing up? The ground. The ground is pushing up. But there are heavy stones and light stones. How does the ground know just how much to push up? Think of yourself standing on the floor. If on the left we think of the floor with no person on it, it turns out when you step on the floor, it sags under your weight. And for a heavy person, it will sag more. And as it is pushed down, the atoms in the floor get closer together, and they push back on you harder. So as you walk through the world is adjusting to your every step, pushing back just enough to keep you from falling through the floor. Think about that. Now, there are occasions when this is not true. If you're walking on thin ice, it might not push back enough to hold you up. And so here's a poem written by Ogden Nash. Some primal termite knocked on wood and tasted it and found it good. And that is why your cousin May fell through the parlor floor today. You see, the termite weakened the floor so it could no longer push back and keep you in equilibrium. Now, there's more to equilibrium than just two forces. They have to be lined up. By looking at this chimney, you can tell it's falling. It's not in equilibrium. It's crashing down. Although the two forces are just about equal, they're not in line. So to be in equilibrium, it takes forces that are in line. They have to be in the right direction. Also, you can think of a pendulum hanging a weight on a string. If you push it to the side, the forces represented by those arrows bring it back into equilibrium at the bottom. Now, these ideas from science, maybe you can apply to your own life as we go through. There's another way to look at equilibrium. Think of a brick. Here are two bricks lying on the ground. And we can think of the energy. Instead of the forces, we can think of this thing called energy, which if you lift up the brick, you know you've done some work to lift it up. And so the height of the brick above the ground is a measure of energy. Well, to tip that brick over, you must push on it and raise it up a little bit on edge before it crashes down again. So the line on the bottom is a graph of the energy. When it's standing upright, it has high energy. It has a high energy, and then, or at A. But to go to the side, it must have even higher energy. So if you push it to the side a little, it comes back. You have to push it far enough to get over the crest of the hill and have it crash down in the lower energy. So we can think of equilibrium as this drawing of hills and valleys. In the bottom of a valley, a ball finds itself in what we call stable equilibrium. Push it to the side, it just comes back. On the top of a hill, a ball is in equilibrium too. But the slightest push to the side, and it's off. It's gone. Now, some valleys of equilibrium, of balance in your life, are deeper than others. We call a shallow one a metastable, barely stable equilibrium. And it takes just a little bit of work to push over the crest of that nearby hill and down to a much lower energy. Perhaps you've found equilibrium. Maybe by doing a little work, by reaching out a little further, you can find a lower equilibrium, a more balanced equilibrium. Well, that idea was applied by scientists to invent something called the laser. Lasers involve atoms that have a very high energy but shallow valley called a metastable state. And astronomers like Saket use these lasers, that yellow laser reaching out into space, to help focus their giant telescopes. And you may think that that's the only use for this idea, but if you've ever played a compact disc player, inside that compact disc player, there's a laser using this idea of metastable energy to help you achieve harmony by listening to music, or maybe even a presentation by His Holiness the Dalai Lama. Well, there's more in space than one dimension. Here's a two-dimensional shape, which we call a saddle. And that's interesting, because in one way, if you push a ball to the side, it will come back to the middle. But the other way, the ball will roll away. So that's unstable. And here's a topographic map which shows you such a saddle. On the top here, if you're used to reading maps, you'll see two mountains with a saddle between them. And on the bottom, there's actually a picture of a crater. That's a deep hole in the ground. And if you form yourself into a ball, you'll roll to the bottom in stable equilibrium. Well, here's a gentleman with a saddle and a ball bearing on the saddle. But I'm going to have you look at the English language side to see a short movie. So here's the saddle, and this gentleman is going to find equilibrium for this ball. Wait, it rolls away. That is an unstable equilibrium. However, what he's going to do next is set that saddle rotating. And when you put the ball in this usually unstable but now rotating structure, it has found stability again. So there's more to stability than just these graphs. Sometimes dynamic motion can help us achieve balance. When I'm running down a mountain from rock to rock, I'm in equilibrium and balance because of dynamics. I'm always changing as I run. This idea applies to astronomy. It applies to astronomy because the Earth, in the middle of this picture is the sun, and off to the right is the Earth. Now the sun is pulling on objects out in space, and so is the Earth. And these points labeled L1, L2, L3, L4, and L5 are places where the sun and the Earth's gravity balance. If you go 1.5 million kilometers towards the sun from the Earth's pulling you towards the Earth. The sun is pulling you towards the sun. But the forces are in balance. That's an equilibrium place. Except if you move towards the Earth's force gets larger and you fall all the way to the Earth. And if you go towards the sun, you fall all the way to the sun. So these seem to be unstable places. Although I'll tell you, astronomers use the one called L1 between the Earth and the sun. We have a satellite there called the Solar Observatory, and it looks at the sun all the time, and the Earth never gets in the way. And by looking at the sun, it warns us of when the sun is going to send a blast of radiation towards the Earth, a blast of radiation that will wipe out all cell phones and all satellite television for a while, so we can adjust our lives. Luckily, the Earth's atmosphere protects us from those blasts, but it doesn't protect our technology from the blasts. Good or bad? I'll ask the monks. Points L4 and L5 are actually stable equilibria, and we can place satellites there and have them orbit around with the Earth. And L2, outside the Earth, it looks away from the sun at the blackness of space and allows us to actually look out in space and back in time to see the Big Bang itself. This is a graph that every one of those dots is an asteroid, a rock in space. The blue lines are the lines for the planets. The sun's in the middle. So from the sun we see Mercury, Venus, Earth, Mars, and then these asteroids. And then the outer circle is Jupiter. And in front of Jupiter in its orbit and behind, there's a cluster of asteroids. Nature has gathered them at these balance points, these equilibrium points called L4 and L5. They're only balanced because the Jupiter is in orbit. It's in motion. Dynamic balance holds this together. Dynamic balance, like these children from the Exploratorium balancing sticks. The stick can be balanced only by continuously moving your hand. And here are two different aircraft. The one on the right is a light aircraft called a Taylorcraft, and I can fly that one. If I let go with my hands, that aircraft will find equilibrium. It will find its balance. It doesn't need me at all. The one on the left, it cannot be flown by any human alone. It is so unstable that without a computer, no human can fly it. And so that's the example of an aircraft that's always out of balance naturally. It can't even be controlled by a human. And it's a warplane. Hopefully some humans can control its use. Let's go back to atoms again. These are hydrogen atoms. And one of my favorite scientists, Richard Feynman, said, all the world is made of atoms, small particles that attract each other when a little ways apart and repel each other when close together. This leads to this graph of equilibrium. Two hydrogen atoms will pull together until they reach the low point, the balance point in equilibrium, where they form a molecule and they remain in balance. And this red line shows you this energy graph. They're in the bottom of the energy. And here's my friend Richard Feynman with his quote, which I'll let you read in Tibetan a little bit. So, inside of these atoms, there are other things which we will go to next. Oh, I should say, here is at the bottom, you are seeing a slab of material that is flying in the air. It's flying in the air and it comes over to a magnet and it bounces off the magnet and goes away. It's very cold. So what's going on here is that there are two electrons, and electrons are negative particles, and they always repel each other. There's no equilibrium for electrons. But when you put these electrons in a crystal of the element lead, the electrons interact with the atoms in the lead, and the lead allows the electrons to form together, to bind together in equilibrium. You might think of this as other objects around, helping two objects which can never reach equilibrium to find equilibrium. And the result of this equilibrium is flying trains. We actually have trains that use these electrons in something called superconductivity to levitate above the rails without touching anything and to fly at hundreds of kilometers an hour near the ground, giving us transportation. But only because those lead atoms are bringing together those impossibly repelling electrons. This can apply in other ways. This is a video on the English side of something called liquid helium. Helium atoms do pull together, but because of something called quantum mechanics, they can never solidify. They are always a liquid, even at this extremely cold temperature, minus 271 degrees Celsius. And at this temperature, the helium remains a liquid. It's called a superfluid. All the atoms, when they're cooled, when they slow down enough, join together in a group equilibrium that gives them properties that we don't see anywhere else. The dripping from the bottom is this liquid crawling over the edge of the vessel, the glass, and coming down the side. Imagine if you had a glass of water and the water crawled over the edge and dropped down the other side. This group gathering to make equilibrium also applies to snowflakes. And if you look at this top picture, you can see 6 blue fuzzy balls. And these blue fuzzy balls are actually microscope images of water molecules. And they form together in a hexagon, a 6-sided figure. This is the world's smallest snowflake. In the bottom is an illustration of what you're seeing. That's an artist's drawing of what you're seeing. But this photo shows you we can actually trace out atoms and molecules. Now the thing is, the slightest disruption breaks apart this snowflake. The more molecules we add together, the more stable that snowflake is. And here I've caught an image of a snowflake that's been caught in a spider web. And it has billions of atoms and molecules in it, and it's quite stable as long as it's cold enough. By the way, I'm a planetary physicist, and what you're seeing here are my photographs of snowflakes that will be made on Mars. This is the Discovery photograph. This is what scientists do. This is the first picture ever taken of snowflakes that I made in a laboratory under Martian conditions. And NASA right now is looking on Mars to find these snowflakes. These snowflakes are made of dry ice, carbon dioxide, and they're cubes with the corners cut off. And let me tell you, as a scientist, I will find great joy if these are discovered on Mars. If I'm a scientist, I will find great joy if I'm wrong. That's the way science is. I will have advanced the knowledge of the world by telling people what to look for. But as a human, I must tell you, I will find more joy if I'm right than I will if I'm wrong. Now, in quantum mechanics, there's something very interesting. It tells us that if we have found equilibrium in space, the walls around us that confine our equilibrium mean that we must always remain in motion. This is called Heisenberg's uncertainty principle. And it says we can never have complete knowledge of the universe. It also says that if we look at something, it changes. For example, in my audience with His Holiness the Dalai Lama, he asked me, what do scientists believe about what happens when we look at an object? Does that change the object? And I could answer him, yes. When we look at an object, it changes the properties of that object. Because to look at an object is to find out where it is within some box. And according to Heisenberg, when you know where something is, more and more precisely, when you take the wide box on the left and you make a narrow box on the right, the particle speeds up its motion. It gains energy because you've trapped it, you've seen where it is. So by knowing where something is, you cannot know how it's moving and where it's going. And that box can get small enough the particle escapes out the top. And that's what helium is doing in liquid helium. As it comes together, it escapes. Now let me give the negative side of science. Nuclei. In the nucleus of the atom, there are protons and neutrons. And like the electrons, they repel at a distance. They don't come together naturally. But in the center of the sun, the heat and pressure forces them together. And when they get close enough, they grab onto each other and they pull into equilibrium. They go over the hump and drop into a deep valley. And here's a graph of that deep valley for all the elements. On the left, at the top, is hydrogen. It's a lone proton by itself. To the right of it and lower down is helium. It has 4 nucleons, 2 protons and 2 neutrons, and they have lower energy. Inside the sun, hydrogens are pushed together to form heliums, And when they do that, they go to a lower equilibrium and they release the energy which powers the sun and brings us light and heat on the earth, allowing us to live. Other stars go on to burn helium and carbon and oxygen, but at the bottom of this curve is iron. And when stars bring together iron, they can no longer make energy. They're at the bottom of all the equilibrium. They die, they collapse, they explode, and they create all the elements to the right, ending up to the right of this diagram with uranium. Uranium releases energy by fissioning, by breaking apart. And when it does that, you have an atomic bomb. When hydrogen comes together and makes helium, that releases energy, and that makes a hydrogen bomb. We have to think as humans, and this is why scientists need philosopher monks, because will we use that combination of hydrogen into helium to make fusion power to power the earth, or will we continue to use it to make nuclear bombs? So here's our choice. Nuclear fusion. Do we use it to power our lives, or do we use it to destroy life? Scientists don't answer that question. We've given you the question. We need to convince the world never to use those weapons. Now, when I look at a cloud, this is a thing called a cloud chamber. That point there is radium. It's decaying, and as it spits out particles, they leave a track in the cloud. This is how we learn about the universe. We do it by looking at tracks. And there's one scientist here named George Gamow, and he discovered that particles trapped in wells can actually get out of the well without going over the top. They can disappear in one place and reappear in another, never crossing the space between. We call that tunneling. It's kind of funny. You'd think it would never be useful. It explains radioactive decay, but if you have a flash drive in your pocket, it works by tunneling. Engineers have figured out how to make electrons disappear from one place and reappear in another and trap them in equilibrium to remember things for you. So sometimes the physics of radioactive decay can be used to change your life. And I'd like to end with one story of science that's a little happier. A cube can be set on the ground in equilibrium on 6 faces. A sphere can be placed in any orientation. But a scientist named Domokos wondered, was there any shape that you could put on a flat surface that would roll over into one position and only one position? And mathematicians doubted that this was possible. So Domokos went to Greece and he picked up thousands of stones and he put them on the ground and to see if he could find one that had a shape that would always roll over. And it didn't work. So he looked for 10 years. And then in 2006, he discovered the answer. There's a shape which he called a gombak, and it's kind of like a helmet. And he made it, and this shape of uniform material, if you put it on a table, it will always roll over and find its balance. And once he found it, he looked in the world to see if he could find that shape. And he found it in India. There's a tortoise called the Indian star tortoise, and it has this shape. Male Indian star tortoises fight each other by turning each other over so their arms are flailing in the air and they will die. But their natural shape returns them to equilibrium. They roll right over and continue fighting over the women. So we have to learn how to find equilibrium in our lives. Even though we have science and engineering, we all need to find the mental balance to use our joy of discovery for good and to make our lives in better balance always.
And let me share my observations from Buddhist viewpoint and also maybe some new knowledges that I learned. Like with regard to the first presentation, I wanted to make one comment from Buddhist perspective, which is quite challenging. There is a quotation from a Buddhist epistemological text where the master says, when you know, or one who knows what is to be discarded, what is to be adopted, is a valid person. So the question is to know what is to be adopted and what is to be discarded, and the question is really not about knowing everything. And if the question is really knowing things at a far off distance with your eye in the universe, then he says you better invite the eagle as your teacher, because the eagle also, without using telescope or anything, is able to see things at a very far distance which human eyes fail to see. So he makes a fun of that point by saying then you better invite the eagle as your teacher if you're interested. So this is a little bit of challenge, you know. While having said that, of course there are a lot of advantages of discovering many things. So during these presentations from the scientists and also from the Buddhist scholars, all of us need to constantly remind ourselves, what am I getting from this presentation for harmony and happiness? For the Buddhist presenters, what am I getting to enrich my Buddhist practice through these scientific knowledges? Similarly to the scientist is, what am I getting from these Buddhist presentations? So in this context, let me make my own small observations. For example, when you made this presentation, I really felt, if I'm wrong, please correct me. He was basically saying, in your life, if you want to achieve equilibrium, either you stand still like a rock, or keep on moving and be active in order to achieve what you want, like the ball on the saddle. Does it make sense?
Yes.
Wonderful. I wanted that confirmation. And then, also it looks like in our daily life, equilibrium is reached sometimes by working very hard, by being dynamic, by making ceaseless effort. It is true that you can make progress, development. But this does not mean to say that you keep on working and don't take rest. So on and off you need to take rest to reach that equilibrium. So if my observation is correct, so such kind of explanation and finding from science really enriches our own spiritual practices. So thank you very much for that. And then the last thing that I wanted to point is that since we are talking so much about harmony and equilibrium, and there are so many wonderful findings and presentations from the scientists, is what I'm really a little bit worried about is we all very clearly know there is now no harmony or equilibrium in the ecological system. The whole ecological system is dying out, waters are getting polluted, snow mountains are melting, horrible things are happening. What are we scientists are doing in practical terms that would make a change in this changing scenario where equilibrium is lost and harmony is lost, and thereby definitely human beings will be without happiness. So this is a question that I want to ask.
So I'll answer the last question first. One of the things that scientists are doing is creating solar power and wind power. And these are powers using the sun, but without creating carbon dioxide, the gases that are warming the planet. And we can only hope that the use of solar power will grow fast enough. And the other thing actually we can use is nuclear fission, although it has its dangers of pollution itself, a different kind of pollution, a radioactive pollution. And the hope that fusion power will be created someday, and we have to worry about what pollution that will bring. So it's a balance. And I'll also add in the idea I had that sometimes you might not be able to find equilibrium by yourself. Sometimes, like the hydrogen atom, it takes a second particle to help you find equilibrium, maybe a teacher. And sometimes it takes an entire society, like the superconductor and the super fluids. It takes us the interaction with many others to help you find equilibrium.
There is, as Sir said correctly, there is one project known as ITER, which is totally based on solar. It's a fusion. So, upcoming energy scenario without releasing any harmful things to into the atmosphere, that may be very much helpful as well. So, it's a international project. In India is also one of the largest partner in that project.
The question is, there are many good people doing small things everywhere, but are we doing enough equal to how much everything is dying? So that is really the question. There are many good people and small things are done in many areas of the world, but are we doing enough to be able to face this really, really awful destruction and death that is happening now today in the world? Are we doing enough? Will we be able to restore the balance?
I don't think we're doing enough. However, at the exhibition the other day, and I encourage you to see the exhibition on climate change, the Buddhist monks have given a recipe for what each of us can do to do our part in pushing the world towards doing enough. It's very difficult. There's tremendous work. I can't see it happening anytime soon. But without each of us starting to work, it'll never happen.
And the Chanyum Golashi to Zambalada, Dujigi Mubuni, Dujigi Mubuni, Mubuchi Konagi Denglani, Chanyumgi, the Shetu the West, Chichero, and the Chigla, the Halore, and the Yugul Machina, and the Temper the Chanyum Chin Dematu Kimsen Karides.
So it's related with equilibrium. Can one single object or one single entity can find equilibrium without depending on other particles or other objects? And the second part of the question is that you showed that clip with saddle and the ball, moving saddle and the ball remaining in the equilibrium. So without that saddle, the handle of that saddle, can that ball find equilibrium?
So I'll answer the ball question first. So the ball question is, no, that ball, if you place it on the top of that saddle and it's not rotating, we look at it, we see where it is. Quantum mechanics assures us that it is moving a little bit. And on a saddle, a little bit of motion moves you to a place where you're going to accelerate away. So without the rotation, that ball will leave that saddle position. And what was the first question? Oh, yes, and a very important question. In the physics view, can a single particle in an empty universe find equilibrium? And that's a philosophical question, but I will tell you that in all of the examples in physics, I'm using two particles, at least two, to find the equilibrium. It may be that one particle generates something called a field, and then the second particle interacts with that field. And to a scientist, what a field is like if you take a magnet and you sprinkle little bits of iron on it, the iron forms lines that look like grass in a field. And those lines are there whether the iron particles are there making it visible or not. So two magnets can find equilibrium by one of them making a field that interacts with the other. But for all the science examples I gave you, it takes at least two particles to make an equilibrium.
tini soso tini kolam di tempo jini yore sungdola tini sola tini pension tunjigi toni dongto meba dang tini dongto mena tini jin la soba gan jungyo marese te jungsen gare la de sola tini koranso do nyamba dang tini chanyon bi wangi yin sungdola tini dang so zamling dila tini yar khala chawa chiro do dang tini gungala dangwa chiro do ya nashin tini nimo da tsemmegi tini da ninsenni di ringdung ki khepracho di jungsen gani tini jungwe namsala.
When you talk about the planets rotating around the sun, you say that they manage to kind of stay in a stable equilibrium condition because their orbit is kind of static and that's why they don't collide and fall apart. But we have this experience of a warm summer and a cold winter. So it seems that the distance between the planet and the suns are changing. So even if the distance are changing, how it keeps the equilibrium. And he also talks about the difference between day and night.
So there's more to a planet going around the sun. We call that revolution. And it revolves around the sun. It goes in its path from year to year. But in addition to that, the planets themselves rotate. That's rotation. And that rotation brings us around so we're on the sunny side during the day and we're on the away from the sun side at night. But summer and winter, it's actually quite interesting. We are closer to the sun because our orbit is not a circle, it's a little bit elliptical. We're closer to the sun, closest to the sun on January 4th each year. That's the middle of the northern hemisphere winter. So it's not the distance to the sun that makes summer and winter. It turns out that the Earth is a top, it's a spinning top, and it has an axle through the middle, sort of imaginary axle, that tips to the side. And when the northern hemisphere tips towards the sun is high in the sky, and that energy hits us full on, straight on, and that warms the earth, which warms the air, which warms us. And during the winter, the tip remains the same, pointed towards the pole star, but now the northern hemisphere points away. We're on the other side of the sun, and we point away from the sun. And that pointing away from the sun means the sun is low in the sky, and the sunlight glances across the surface of the earth, bringing less energy to each of us and making winter. So what I was presenting was the simple story of just the revolution of the heavenly bodies, not the full story of the rotations and the tilts. And I have a saying I'm known for, which is, it's more complicated than that. And when I'm teaching students, I start out with the simple level, and then as they ask questions, I escalate to the more complicated level. And I've been told by Buddhist scholars answering my questions on Buddhism that it's more complicated than that.
I thoroughly enjoyed the talk of Dr. Paul. One can see that he has biologized the rhythm of science which he has seen in the atoms, molecules, in the planet. And that is actually the aim of a scientist, that he has biologized it. In his body language you can see it. The same purpose is in the monkhood. When a monk sees the poise, the might, the rhythm, the perfectness of his deity, he also imbibes and biologizes all those things in his body. Now the purpose of the science and the purpose of the monkhood in this sense is same. Now what is the use of doing all science? Science makes a breakthrough once in 100 years roughly. Similarly, even in the monkhood, you get breakthrough once in 100 years. Buddha does not come every time. One Buddha comes and following that and another Buddha came. So breakthrough, if you expect, either in science or in monkhood, it takes about hundreds of years of research. However, I will place monkhood in a superior position in one sense, because science does not look at the ethical part, so that the same hydrogen atom can be, same hydrogen molecule can be made into an hydrogen bomb. Here comes the spirituality which deals with the ethics, the monkhood which deals with the ethics and perfection in ethics, which can help science to grow beyond this self-destructive mode. Thank you.